This paper is check now low power violations by using machine learning based classifier. Abstract. The violation check process for design verification often requires designers to manually inspect and identify the design issues. As the complexity of the design increases, the overwhelming the workload during the time-limited violation review process may jeopardize the correction for the RTL code and induce the engineering change order ECO. In this paper, we present a practical solution with machine learning techniques that learn to identify highly dubious violations from the historical violation data and reduce the effort of manual review of ignorable violation. We leverage the ensemble the XGBoost model with the bag-of-words BOW representation and well-defined features to optimization learning performance. The empirical study on the 3 different designs demonstrated that we can reduce at least the 12% review effort without the human expert involvement. Also, we can reduce the false alarms and the largest reduction of total violation reached up to 50%. Introduction. To verify a design, simulation-based techniques are most popular approaches. The simulations are iteratively conducted to ensure its correct functionality and behavior before design tape-out. While the simulator runs various checks on the design, the violations are put to flag suspicious conditions. In each simulation iteration, designers manually review the violation, which are either waivable violation, false alarm, or the true design issues that must be fixed as mentioned in the reference 1. The figure 1 shows the violation check flow. The review process requires cross-team expertise of the design domain, knowledge, and lots of time to investigate violations. As the complexity of the design increases, the number of the violation increases, so that the dramatically increased workload of a manual review process usually lets the time-limit violation check process remain unfinished. In the end, the design issues may fail to be observed after RTL freeze. Designers need to implement the design engineering change order ECO to fix these design issues, and it may postpone the tape-out process. Inspired by the spam filtering problems, we formulated the violation check process as a supervised binary classification problem. The spam email filtering is one of the classic machine learning ML applications. These ML techniques have the capacity to learn and identify spam mails and phishing messages by analyzing the content of the emails and messages throughout a vast collection of computers. The violations in IC design check flow are also composed of the text, and the words in the signals usually represent certain physical characteristics. Therefore, we apply the ML techniques to learn how to identify highly dubious violations from the historical violation data and reduce the effort of manual review on ignorable violations. In these papers, we take isolation clamp value check process, one of the low-power check items to inspect the correct isolation cell ties between 2 power domains. As an example to demonstrate our solution, as figure 2 shows in the training stage. We implement the ML method to learn artificial intelligence AI checkers that inherit and integrate the experience of the design domain experts across time and various design architectures. In the inference stage, we use AI checkers to classify violations into waivable or high-risk violation to reduce false alarm violations. Finally, the validated levels of the inspected violations can be used for incremental learning. Experiment shows that it can discover all true design issues in predicted high-risk violations, and the number of total violations can be reduced up to 50% to achieve the shift left of design issues, as figure 3 shows. Figure 1 is the iterative violation check flow. The figure 2 is the ML-based violation check flow. Figure 3 is the illustration of the design issues left left. Approaches. In this section, we introduce our ML-based approach in more detail. It consists of three steps, including data preprocessing and feature engineering and ensemble modeling. To learn on an AI checker, the proposed approach is illustrated in Figure 4. In the data preprocessing phase, we describe how to represent violation logs using a bag of words as vectors and convert these vectors as a documented term, metric, DTM. And during the engineering phase, we create generalized features that allow the models to learn violations of different designs effectively. We illustrated the concept and implementation steps of a new feature generation. In the model construction phase, we described how to optimize the model performance through machine learning techniques. We designed an ensemble method to split the data for modeling training and vote for the highest probability as a final prediction. Figure 4. The overall flow of proposed approach. A. Data pre-processing. The purpose of this step is to convert data into a format that can be learned by the machine learning models. First, we tokenized violation logs and removed the noise such as about word capital and digit and special punctuations. Then we presented the unstructured violations with the structures of BOW features as the input for ML model. Tokenization. Tokenization is a technique that is used to segment a string into substring. We apply the word tokenization to separate each violation signals as set of the representative volumes called tokens. The signal log shows an example of word tokenization where the input of a low power check violation signal is common 1, common 2, A1, B2, G3, D4, E5. And the expected tokenization result is common 1, common 2, AY1, A1, B2, D3, D4, E5. So text cleaning. The goal of this step is to remove the irrelevant information from signal tokens. Typically, it is customized based on the design domain knowledge. In this paper, we first apply the text normalization to lowercase text. Next, the common prefix tokens are eliminated to prevent the model from the learning noises. Also, numbers or special symbols such as square brackets in the token are removed. Some convention of naming rules should be aligned in case of misleading models. The example of signal token is common 1, common 2, A1, B2, G3, D4, E5. So the expected result of this example is A, B, C, D, E. The common prefix token, square brackets, and digits are removed. Second, we lowercase all tokens. 3. BOW construction. Machine learning algorithms can't work with the raw text directly, so that the text must be converted into numbers or specifically speaking, vectors of numbers. A bag of words, BOW, is a representation of text that describes the occurrence of a word within a document. So we use it encoding each violation log. So to construct BOW vectors, we collect a vocabulary of known tokens and measure the token occurrence for each violation log. These BOW vectors of violations can be further organized as a DTM for training ML models. So the example of the BOW and DTM construction are described as follows. Assume that we have 3 lists of pre-processed violation logs. So we first construct the vocabulary, which is a list of unique signals token. So now, next, we count the occurrence of tokens and each violation log and encoded it as a BOW vector. Taking the first violation as an example, we can get a vector token count in a construction vocabulary. After encoding a violation log, we further organize these BOW vectors as a DTM as the table 1 shows. Table 1, violation like these, and then B, feature engineering. The purpose in this step is to help model learn more generalized patterns of violation. For different designs, the token composition and the sequence of violations are not identical. Feature engineering is extracting meaningful information from data. It takes features more informative and discriminative across the different designs, increases ML models, generalization ability, and robustness. Based on the observation of isolation violations, if new signal tokens are observed, it will increase the risk of discovering true design issues, and the feature called the novelty feature is produced by comparing the data from the new design and the historical waived violations. Furthermore, the feature called token cluster feature is generated by performing the clustering analysis of tokens designed signals as new features. 1. Novelty features. We define a new token which do not appear in the historical tokens as novelties. The located novelty tokens, we construct a distinct token set from the historical waived violation and new design violations and compare the differences between them. Only tokens that appear in the new design will be defined as novelty tokens. The illustration is shown in figure 5. We created a binary vector that a value is 1 if there is any novelty tokens in the violation, otherwise 0. As a result, each violation has a value to reveal each novelty status, which is illustrated in figure 6. On the other hand, in the training data from the historical designs and the novelty features is obtained by comparing the distinct tokens on true design issues and waived violation, so that the model is learn how to judge the violations with the novelty tokens. Figure 5 is the defined set of novelty tokens, distinct tokens of historical design and distinct tokens of the new design, and novelty tokens. So the figure 6 is an illustration of novelty token feature. 2. Token cluster feature. When constructed DTM for ML modeling, we use common tokens to align a training and test feature sets, and the tokens that only exist in the training or testing dataset are valid for modeling. So they call the non-common tokens. If we don't utilize non-common tokens during the DTM construction, the non-common tokens with the similar word structures are consequently dropped. So that means we may lose important information because the tokens shared with the similar word structures usually have a similar physical significance. Thus, we created token cluster features to utilize non-common tokens so that the model can learn more patterns in addition to the common tokens that exist in the first place. The process of the token cluster feature generation is described as follows. We first encoded a non-common tokens to BOW vectors by segmenting each token to letters. Each dimension represents our character in alphabet. Take the word apple as an example. The character's level BOW vector is obtained in Table 2. Table 2. We conducted the k-means clustering algorithm on these character level BOW vectors and group all tokens with similar word structures. Each token is encoded by the chip cluster it belongs. Finally, we measure the occurrences of the clusters for a non-common token in each violation and generate the cluster level BOW vectors to construct the features. An example is shown in the Table 3. An example of token cluster features. C. Ensemble model. This step explains the process of the modeling learning. Different from the general natural language, design signals are quite domain-specific, which make them no semantic. It's not suitable to enhance model performance via any pre-trained NLP models in the current studies. Therefore, we applied XGB-boost algorithms as our base models and conduct the ensemble techniques to best combine the predictions. Ensemble model is a technique where the multiple diverse models are created to predict an outcome. It enhances not only the model's performance but its generalization ability. We conduct the cross-validation with the prepared dataset for modeling training. One round of cross-validation partitioning data into complementary subsets that consist of training and test sets. We perform an unfold cross-validation to train-based models using SG-boost algorithms. In the end, there are several inferred candidate probability for each violation, and the largest one. The violation with the highest risk is chosen for the final prediction output. We illustrated it shown in Figure 7. The Figure 7 is the illustration of ensemble models mechanism. Experimental result, Section 3. We applied the proposed approach to isolation clamp value check process of three different low-power designs A, B, C. Table 4 is showed the total number of violations and true design issues for the testing designs and the training data, which were collected from the other designs' isolation check process. These violations were generated by simulation tools during a project's development, so in addition to the isolation check used in this empirical study, other types of the checks that have violation signals consisting of tokens of text are or potentially applicable using our proposed approach. That is Table 4. The total number of violations and true design issues of experimental data sets. SD. The train AI checkers using the proposed approach. The training of the AI checker required violations of historical and new designs to participate in the process. Retesting the design would share the same training data. In the data preprocessing stage, we compared each testing design and with the training data to obtain common tokens. These common tokens were used to constrain the DTM dimensions that would be used for model training and inference. The number of words and common tokens of preprocessed training and test data were shown in Table 5. Table 5. Number of the words and common tokens for training and testing designs. The number of common tokens used in modeling was less than the number of words in the testing data due to the differences in the violation of training and testing designs. Therefore, we need feature engineering to extract more information and make efficient use of non-common tokens. In the feature engineering stage, based on a preprocessed DTM, we compare the training and testing data to generate an average tokens feature, which occupied one dimension. The cluster token features were derived from non-common tokens. The dimension of the features were all set to 30. In the ensemble model stage, we used XGBoost models with the same parameters for each design. We performed 5-fold cross-validation on data and trained 5 models based on the training data subsets. Which test violation was inferred by these models, and a highest probability was chosen as a prediction result. We defined 0.5 as the threshold. If the prediction probability was greater than 0.5, the violation was judged as a high-risk violation. Otherwise, it was a low-risk violation. For each design, the total time of the pre-processing and feature engineering, the training and inference is 5 minutes and 2 core CPU. We use the same pre-processing procedure and a model setting during training stage. So the reviewing the ISO clamp check using AI checker. We presented the evaluation study and the proposed approach that gave an intuition of each behavior and performance. For reproducibility, we run each configuration over 5 seats and report the average performance. We train a supportive vector machine SVM models, a classic machine learning algorithm for classification problems, as the benchmark-based model. We compare the different performance brought by each step. Table 6 shows the experimental configuration. Table 6 is the experimental configuration for the evaluation study. So we demonstrated the effectiveness of the techniques. With the proposed AI checker, the recall rate denoted the ratio of the number of the true design issues and predicted a high risk violation divided by the number of the total true design issues. The recall rate 1 indicates the predicted high risk violations contain all true design issues. On the other hand, the review reduction rate represented the percentage of eliminated low risk violation from the review process. Figure 8 presented in the result of the recall rate and violation reduction rate in different most designs and configuration. The proposed approaches, configuration 5, outperforms the other configuration. I reached recall rate 1 in the all testing designs A and B and C. We could observe that more methods joined in. The recall rate was closer to 1 and the review reduction rate went down. There was a trade-off between the recall and the review reduction rate. Thus, we might have more false alarms to capture all true design issues. In real-world application, we needed to satisfy multiple objective scenarios and consideration to change in both recall and review the reduction rate. In particular, the number of the to be reviewed violation decreased while keeping the constraint that a recall rate was 1. In the end, we could achieve the 50% and 12% and 18% review reduction for design A, B, C. The recall rate and review reduction rate of different configuration for 3 testing designs. So the conclusion, this work proposed an approach that applied ML techniques to assist the violation review process and represented empirical study on the isolation check. The result demonstrated that we could reduce at least the 12% review effort without a human expert's involvement while keeping all true design issues detected. Moreover, it helped reduce false alarms and the largest reduction of the total violations reached up to 50%. It also achieved a shift left of true design issues, so main experts could tackle the issue earlier. The result showed that the ML model could learn the experiences and knowledge of reviewing violation by domain experts from historical data. We could also train the model incrementally using the accumulated historical data, hopefully starting from the promising experimental result of the 3 designs. The proposed AI checkers can be generally applied to other design check flow in the future. Okay, thank you. Today, thank you for your time and see you next time. Today, I read this paper, the check low power violations by using the machine learning based classifiers. Thank you again.